Are you doing it? You want to say hi, Mom?
Hi.
Hi, Mom. What do you think? Do you need another minute? Or no? No, you should try to do this without any special calculator features. Just because, guys, just because. Especially to tick off the people in stack. Yeah, I'll call on people randomly for A and B. And the other ones are a little more challenging, so maybe we'll have volunteers on those. This is quite a coin, isn't it? No one would notice if you had this coin, I'm sure.
Wait, would it be 9 times the width on one side?
Yeah, I don't know how this would be made. I don't know that you could make a coin like this.
It would be.
It really wouldn't be a coin. I don't know how you do it. Just go with it, okay?
Yeah, no, you just put extra weight on one side.
Yeah, but that'd be very disappointing.
How much extra weight would you need?
That would make a great IA, wouldn't it? How would you make a weighted coin? You apply a lot of interesting so that the probability is 0.9.
You could use different metals. No, you could well, or you could like roll 2 different metals together, one the lighter, one the heavier.
I know, but like I said, how much of which would control for how much, how that affects the probability? Can we get a graph of how much weight you add to one side, and then the probability is sitting on the side? Is it linear? It's fine. It's clearly not linear, because that's an axis, so it's probably that one. Probably can't go above one. There might be. Okay, go back and do another IA on that. All right, let's hear from my favorite student. That's right, Matthias. Okay. That's right. I forgot that you were my favorite student. There you go. Okay. So how do we do part A? What's that?
Is it just 9 over 10 to the 20th?
9 over 10 to the 20th. You got it. 0.9 to the 20th. Which did you actually compute what that is?
It was like something like 0.1215.
0.12.
Yeah, 1 to 1.
So, all right, so 3 sig figs, we'll say about 12.2%. Okay, great. And my other favorite student, the next one, these are not, I think these are not too bad. What do you think for the second one there?
0.1 to the 20?
Right, exactly. Right. These are the first ones. Like I said, I feel okay calling on people, and I don't even know what that is. It's something.
1 times
Basically.
negative 20.
Yeah, it's something. It's basically not going to happen, right? Okay. 0.0000. Okay, very good. So those first two are not bad. For the next two, I'd like to take some volunteers though, if you can help us through. In fact, this should, I hope, feel like yesterday's warm-up, right? Go back and look at yesterday's warm-up if you need a tip. And think about the nuance of this easy to ask question, exactly 17 heads. Okay, I want to see some other hands though. We heard from Philip recently?
I'm sure we have
I mean, you can speak up. Go ahead. See it. And Ashish in the background is checking you, so. Okay? He's going to keep you honest. And David over here, he has his hand up too. So they're going to agree or disagree with you.
Is it 0.9 to the 17th times 0.1?
0.9 to the 17th times 0.1 cubed. Okay, so this is like word for word the discussion we had yesterday. This is the probability of something interesting, but it is not quite what we want. But we're going to keep it here for a second, right? This is the probability of, say, getting 17. If someone asks you, if we're going to flip a coin 20 times in succession, what's the probability of getting 17 heads followed by 3 tails? And that is the probability of what you've just calculated. But we can do that multiple ways is the point, right? Like, so this is one of those things that could happen, 17 heads followed by 3 tails. But what else could happen, you know? And how do we account for all the different ways of doing that? 20 choose 7 or 20 choose 3, either one, right? Exactly. And we talked about 2 ways of computing that. You could think about that as the number, also as the number of arrangements of the word H, 17 H's and 3 T's, right? Can you imagine 17 H's and 3 T's in front of you? consider the arrangements of those 20 letters, that word, right? And wouldn't that be 20 factorial? Over 17 factorial, 3 factorial. So a couple ways to think about why this comes out to be 2217. Ways of doing it. Does it make sense, though, why we have to multiply that? This is tricky. There's a lot going on in this calculation. And then whatever we get is what we're going to get. Go ahead, Andrew.
Why would you not choose?
Same thing.
I mean, you could do 22-3 instead if you want. They're the same thing. But not both, right? Because as soon as it would make sense to, you mean like also multiply by 22-3? Yeah. It would make sense to do that if after choosing 17 of the 20, we have 20 slots ready, we're gonna fill. Once we fill we have a choice of 17 ways of picking 17 slots, right? To be heads. And once we made that decision, we would also have to multiply by something else if we had some other choice to make. But once you've made the choice of which 17 of the 20 are going to be heads, you have already made the choice of where the tails will be, right? Does that make sense? So you don't have to multiply by anything else.
Hey, I don't understand why that means that like the heads positions are also chosen.
Why the heads positions are also, why the tails positions are also chosen? Yeah, so this is like, harken back to the warm-up we did a while ago where we had two people dividing pencils among them, or dividing, what were they? I don't remember. Crayons or something, I don't know.
Oh, there were colored pencils.
Colored pencils? Okay.
Pencils with like interesting design.
And
Okay,
ones
whatever,
with
anyway, they were
numbers.
dividing, I don't even remember how many there were 15.
9 and 6.
Okay, okay, whatever. There are 9 pencils and we're dividing them among you and me. How many ways are there to do that, right? For me to choose, what was it? For me to take 5, 6 and you to choose 9 of the 15 or something, I don't know what it was. Let's say there were 15. And the answer is not, I think a lot of people have said that when we had the same conversation, right? We said, how many ways are there to do that? The answer is 15 choose 9, right? But not 15 choose 9 times 15 choose 6, right? Because once I've chosen my pencils, you have nothing left to do, sorry, right? That's the number of ways to do it, done. So the same thing applies here. Like I said, I mean, if you don't believe me, the other way to think about this is, isn't this 20 factorial over 17 factorial, 3 factorial? Isn't that the number of arrangements of the word containing 17 H's and 3 T's? Right? 20 factorial, but then divided by, thinking about the symmetry. Think about how we did aardvark or bookkeeper. Isn't that how many arrangements? Okay. Couple ways to think about why that's coefficient needs to be here. Okay, exactly 17 heads. So what does that come out to? Someone? 0.190. Okay, so 3 sig figs. And then 17 or more heads. Talk us through that one then. What do we mean there? What's the computation we have to do? A little bit laborious, but we can do it. Okay, Ashish.
What's the process from C plus 20 is 18 times 0.9 to the 18th power times 1 to the second power, and then you do it with 19 and 1.
Right, so this is you hear what he's saying? This is the probability of getting 17 or 18 or 19. You see what I'm saying about being laborious? It's a little bit of a tedious process. To the 1 plus, and then we could write at the end 20 choose 20 times 0.9 to the 20th times 0.1 to the 0, or we could just write 0.9 to the 20th. It's the answer from part A, right? 20 choose 20 is just 1. 0.1 to the 0 is also just 1, so we don't need those other pieces if we don't want, but they're there if you want. Okay, so did anyone compute this? I don't know. You're in the process. Maybe we could write a computer program to do this for us. It's systematic, right? The teller can tell me in a second, and you guys do it too. Someone else hopefully is doing it. My stat people with the magic wand in their back pocket can tell us as well whether it confirms their result. Point 867. Can you confirm that, someone? All right. Cool. Okay. Yeah, well, if you understand what we just did, then you've almost kind of covered the lesson that we did today. Okay. So before we go further in the lesson, do you want to ask any homework questions? So that you can be famous someday. Yeah, talk about it. You can be famous. Say, hi, Mom. Yeah. So that you can watch this again over and over again.
I actually watched the third video like 2 times.
Wow, that's really good.
Well, it was really
Or it was really bad and you had to watch it 30 times.
No. It was a good video. I was just really tired. I mean, I love the math.
So any questions on this homework? It's like little 1-page homework I gave you. I didn't come around and check it, so I didn't really see how you guys did, but did you do okay? Interesting questions, right? And I like you're handing some of this stuff, just, right to your calculator. On number 3, you actually have to derive that probability distribution first, which is okay though, right? You're coming up with that. Maybe, kind of, sort of. All right, no one has any questions, is what I'm hearing. Okay, that's perfectly okay. Sheesh.
For number 3 in the table,
Yeah.
if you have 1 as x, you have to do like 2 choose 1, and then find the probability if they like do it twice. 2 different ways you can get like.
We're wondering how many ways are there when we roll 2 dice to get 2 6s, right?
Yeah.
So isn't that only 1 out of 36?
No, for when x equals 1, so like you have 1 dice is 5
Oh, yeah.
times.
Right. So 1036 is the middle one.
Yeah.
Yeah.
It's like-
You're asking how we got that?
When you do the probability, it's 5, 6 times 1, 6, right? But then you have to multiply
Sure.
that by 2.
Yeah. There are a couple ways you could think that through, but sure, the way you just said it is a fine way to do it. Absolutely. Here's another way to cheat on this one, right? The probability of getting 2 6s is 1 out of 36. I think everyone's clear on that. 1 6 times 1 6. What's the probability of getting no 6s? 2 in a row, no 6s. 5 6 times 5 6, and then the middle probability has to be whatever's left over, right? So we don't have to think about what you said, but it should work out. Yeah. All right. All right, so today we are going to talk about binomial probability. You guys are like, after doing all this stuff with distributions and expected value and variance, and you've got conditional probability under your belt, you have so much you are like a probability ninja at this point, okay? Today's our last lecture on probability, and after today you will be a probability master, okay? Okay? There is more one could say, but you will have mastered a large body of, I think, pretty intense and mature mathematics here as far as probability is concerned, right? At the beginning of this unit, you probably were like, oh, probability, cute, right? But now I hope you understand that like probability is deep and interesting and difficult and nuanced and can go even deeper than what we're going to do here. So binomial probability is what this is going to be called today. Before I show you the first slide of our presentation, I want to go back to our warm-up for a second and ask you if this looks familiar to you. This piece here that we wrote down here for part D of this should have, even though we're doing probability, a little while ago we did something that felt and looked very similar. Do you remember what that was? This should look very expanding binomials. Okay, so that may be why this is called binomial probability. In fact, we're going to make a little connection here that's going to blow your mind, right? But do you see this? Do you remember doing this? Like, doesn't this feel a little bit like when you were expanding a binomial? These are the terms of a binomial expansion. We had 2217 times like x to the 17th, y to the 3rd, right, etc. All right, so maybe you didn't notice that, but I hope this felt a little bit weirdly familiar. Deja vu, kind of like, wait, what? Okay, maybe I've done this before a little bit. Okay, so that's exactly how we're going to define, in fact, the binomial distribution today. Okay. So we have to kind of explain what this is saying. So suppose we have an event consists of n independent trials with 2 outcomes. All the trials are repeated with the exact same probability. Every time, the same probabilities of both events. We're going to label one event success, like maybe in the warm-up we call that the head, and failure being tails, okay, or something like that. So I put those in quotes because like later we're going to use success will be like engine failures on an airplane or something like that, and like So success is maybe a little bit of a dubious way to say that, right? You're like, or like, you know, whatever, you'll see. We have defective widgets or something is the first example we're going to do, right, in a minute. And success will be like getting a defective widget. Okay, I just want to make sure you're clear why I have the quotes around success and failure, just labels. So if one event has probability P, and the other has a probability 1 minus P, okay? So there's only two outcomes. Then, this is the part that's a little weird, the terms in this expansion, P plus Q to the n, give the probabilities of exactly however many trials we want. Some number in between 0 and n, right? 17 out of the 20 trials, say. Right? That's one of the terms of the binomial expansion. Okay, easiest to see with another example. Though, this example I don't think is any more difficult than the warm-up, right? So let's read this together here. Let's just say something about widgets. We love widgets in math. In a factory that produces widgets, we've got 0.8% of widgets that are defective. So what's the probability that we have exactly 3 widgets? And let's write that here. Maybe it should be more clearly said, but exactly 3 widgets. And this is important because when I say exactly 3 widgets are defective, I also mean, and it says, if we pull 150 off the production line. So I'm implying here, even though it doesn't say it, that when I pull 3 off the line, I'm getting 3 defective, 150 off the line, I'm getting exactly 3 that are defective. And also 147 that are perfectly fine. Okay, we need to account for that. Just like in the warm-up, right? 17 heads also implies that we have 3 tails in that warm-up problem, right? So it's just to be clear. All right, can we identify all the pieces of this puzzle here? We have the probability of like success, again, a little weird to say that, but the probability of success of having a defective widget when you pull 1 widget off the line is our p-value, which would be what here? 0.008, yeah, everyone catch that? We have n equals 150 widgets, okay? And we'd like to know about, in particular, we'd like to ask about exactly 3 widgets, okay? So those, the p and the n here correspond exactly to the p and the n up above. And we can also write down what q is, right? Q is 1 minus p. This is the probability of getting one that does work. And that would be just 1 minus 0.008, so 0.992. All right, so here we go. Are you ready? We have the information written down, just like the warm-up. How's this going to go? We want 3 widgets to be defective, so those are independent probabilities, so we'll multiply. We want 147 of them to be working. Right? Do you see that this is, I hope, the same? Hopefully you're seeing this is the same as the warm-up. But then how many ways can we do that? It could be 3 defective followed by 147 successful good widgets. Or it could be the first widget is defective and the next 147 are good and the last 2 are defective. That would be a good way to do it. How many ways are there to do it? Something, right? Something, choose something. Say it louder, Andrew. Yeah, 150, choose 3, or 150, choose 147 would be a fine way to say it too. Right? Very good. So what does that come out to? I don't know. Someone tell us. So I hope you see where we're getting this stuff. This is n, choose our whatever our x value we're interested in is, times p to the x, times q to the n minus x. Just like our binomial expansion formula, right? Use the binomial theorem. So that's where this is coming from, in like a general way. What's the, what does that come out to? Someone have that yet? There you go. Volunteer. Yeah.
0.0867.
Someone confirm this. Say it one more time. 0.0867.
Yeah, 0.0867.
867. Did I say that right? Did you get it right? Very good. Someone double check?
Yeah.
All right, cool. Beautiful. All right, moving smartly along. Questions, comments so far? Let's pause and breathe for a second. By the way, this is a little weird here because what does the expansion come out to be? P plus Q, if you were to like actually expand it all the way out, what is P plus Q? It's 1. So it seems a little weird to be expanding this because what does this actually equal? 1, the whole expansion, if you were to do all of them, that is, if you were to add up all of the terms of this expansion, it would be 1. Because when you're expanding, right? Which should, it's not like a flaw in the process, that should make perfect sense that that's happening, right? Because what we have here is, we haven't said it properly yet, but we really do have what we have is a probability distribution, right? If x is 0, we have a probability of that happening. If x is 1, we have a probability of that happening. If x is 2, we have a probability. If x is 3, we have this probability. And we have we have probabilities of x equals 0 all the way up to x equals 150, right? And that would be a proper probability distribution, wouldn't it? It'd be a big table to write out, but that's what it would be. So, hopefully it makes sense that if you were to add them all up in that table, you would get 1. All right, so given the fact that we have a distribution, don't we have a distribution? Isn't it fair to ask of this distribution, if you were to write out this table, wouldn't it be fair for me to ask, what's the expected value and the variance? Of course it would be, right? So I'll just tell them to you. I'm going to provide, just because this is not the context or the class to prove this result, it's not actually too bad to prove though. I'm going to just tell you the variance is NP, you could write this another way, NP Q, right, in the language of the last slide. That's maybe a little bit hard to see. The expected value, though, is easy to convince you of that formula. Though algebraically, again, it might take a little work to prove that, but that's not too bad. Why does that make intuitive sense? Well, look at this last example again, down here. This is the same example as before. I'm just asking you to compute the expected value variance. It should just make sense. Before, forget anything I've said today. If someone were to say, hey, I've got this factory, I'm going to pull 150 widgets off of the production line, and the chance of every widget being defective is 0.8%. How many widgets do you think would you expect are defective? What would you say? Forget the formulas. What would you say? You'd say, well, yeah, you'd say I'd expect 0.8% of them to be defective, right? Because on average, that's exactly what we need, right? So I think this is the expected value is pretty intuitive. I don't need to justify that, but this is a little mysterious, the variance. So expected value from the last problem is 150n, here's what that is, times p, which is 0.008, and someone can tell me what that is. And the variance will be NPQ, 150 times 0.08008 times 0.992. Okay, right? And those two things are 1.2 and 1.2 and 1.1904. All right, good. Beautiful. And again, let's emphasize one more time about expected value. Does this mean that when we go to pull a widget off of the line, that we expect when we expect it to, excuse me, when we pull 150 widgets off the line, that we expect there to be 1.2 widgets on that one draw? That's not even possible. I want to be clear, right? But no, we're saying if we were to do this every day pull 150 widgets off the line, then tomorrow pull 150 widgets. In the long run, on average, every day, on average, we would expect to see 1.2 widgets that are defective. Okay? Comments about that? All right. You all right? This one is so similar to the warm-up and so similar to the last couple of problems, I'd like you to just do this. Ready? I will, in a minute, I'll just write the 3 answers up here, and unless you need to see the work, I won't give it to you. We just want to kind of do a little assessment here, right? Check and make sure you're not crazy. Try it. Ready to go. Free throw percentages. Classic binomial problem, right? Suppose Alex is always throwing with this exact percentage. I'll do it too. Oh my God. It's really good, isn't it? Sorry, I'm unreasonably good. I'm gonna write the answers up, but don't look up here unless you're done. Right, unless you're done. You don't want to spoil it for yourself. If you've done it, you can look up here. Don't check your answers so you try it yourself. If you need to see my work on one of those, I'd be happy to show you. But it's similar to the ones we've already done. Okay, anyone having trouble coming up with those? Help your neighbor. Okay. You know a second, or I'm gonna, unless you have something else to say about Alex, I'm gonna look to the next example. I don't mean this to be interesting, just kind of more practical. Someone, by the way, confirmed that these are the answers you're getting. Is someone giving you the answers? Okay, good. All right, I'm not crazy. Good. Or at least not for that reason. Okay, all right, I'm moving on. Let's wave wildly if you need another second to think about this. Okay. This one needs to be updated maybe for the time, so I apologize. Maybe we need to update this to texting or something. It says, a magazine reports that 6% of American drivers read the newspaper while driving. Okay, I'm sure this is something that like your grandfather did. Let's just, yeah, who reads newspaper, period, first of all, right? And then also while driving. Yes. If we change it to texting though, that needs to be like, instead 6 of 6, it needs to be like 60% probably, right? So, whatever. Reading the newspaper is equally crazy, probably, to texting.
I think it's worse.
Well, that's true, yeah.
Oh, what if you put it on your steering wheel?
Yeah.
All right, I can see that this will provide an interesting discussion for the rest of your day. All right.
Well, newspapers is the thing that they're
Let's see, if 300 drivers are selected at random, find the probability that they 25 say they read the newspaper, and then at least 25 say they read the newspaper as well. All right, so I'm going to write out the answers to these, and there's not much to say about how to do this. Is very similar to the last problem, right? But there will be one snag along the way, and I will share it when we get there. You'll see right away what the issue is. So we have n is 300. That's number of drivers, okay, that we're going to select randomly, and the probability that one of them is a newspaper driver is 0.06. And we care about 25, it says. All right, we want to know what's probably exactly 25 do. So I think by now, I'm just going to write it out, assuming that you're all with me, right? Because I think you're all. 300 n, choose x, 25, times 0.06 to the 25, 0.94 to the 275, and that equals something. I don't know what. I don't actually care to know, actually. Okay, so far so good. That was part A. And part B then says at least 25. So what does that mean? Oh, you see the snag already? Okay, great. So, okay, here we go. You guys don't have anything to do for the rest of the day, do you? Okay. All right, is it clear though that this is what I'm supposed to be doing? Right? This is in fact what we're supposed to be doing. Like I said, you didn't have any plans for the rest of the day, did you? All right, there we go. Dot, dot, dot. Okay. But I want to make sure it's clear in our minds that this, if we can do it, is the sum we're looking for. Do you agree? All the way up from 25, 26, all the way up to 300. 300, choose 300 times. Okay? Yeah. Okay, so that's clear in our minds what we want. And there is a little bit of a shortcut. It's not much of one, right? There is a little bit of a shortcut. What is, if we were to go 300, choose 0, all the way up to 300, you know that all of that adds up to 1. So, yeah, say it again, David.
1 minus the probability of 1
0. 1, 2, all the way up to 20. 4, so you can compute that. That's a little easier. That's only 25 things to add up. Come on. And then you could do 1 minus that, right? It's a little easier. Don't make me do that. Okay, yeah, so we're going to, the staff people in the room know what we're about to do. I'm going to teach you a feature on the calculator that does this. But let's make sure we understand that at no time is this like a magic black box. It is just doing this work for you, okay? You could teach a computer to do this, and somebody already has. Perfect, okay. So let's talk about this one first. But let's do A as first. I'm going to show you how to do A on the calculator without, using this. There's a feature on your calculator called Binomial PDF, okay? And it's available if you, for my staff people here. We need to go to vars. Instead of vars, second vars, there's this DISTR, right? That stands for distribution. And it has all sorts of interesting distributions on it. But the one we're concerned about right now is Binomial PDF, which stands for, that's a good name for it, Binomial Probability Distribution Function, right? I'd actually prefer, I think, probability mass function, based on my discussion of that idea at the beginning of this. Okay, so try that, Binomial PDF, and what we're going to write is Binomial PDF. Binomial PDF takes the following arguments. N, comma, P, comma, X. And I've already written these nicely out for you, haven't I? Okay, here we go, in that order. So on your calculator, try this. 300, comma, 0.06, comma, 25. And see if you don't get the same thing that, so a lot of you, did anyone do this already up here? Okay, and see if you don't get the same answer you already did, namely, well, here, I have it right here. I can do it myself. 300, 0.06, comma, 25. Did everyone get 0.0226? 0. Oops. Yes? All right, whether you do it this way or this way. Is this a huge time saver? Not really. Not really. Before we talk about the other feature that's going to help us get this one, though, let's describe, I want to make sure you're clear. Remember I told you could write out you could actually write out the binomial distribution? X equals 0, probability, what is that? X equals 1, what's the probability of that? You're making a table, right? All the way up to x equals 300, what's the probability of that? It would be a very large table. And couldn't you also, just for fun, visualize it with a histogram? Wouldn't it be fun to visualize it with a histogram? And the histogram would look maybe something like this, right? Does that make sense? Right? Wouldn't a histogram look something like that? Except 300 bars, each with some probability as its height. Does that make sense? Yes? So what does this compute? This computes the area of just 1 bar of that distribution. Isn't that what that does? What we'd like to do for the second part is to compute okay, that's my sloppy histogram, is not just the area of that 1 bar, but we'd like to sum them up, okay? So we add up a whole bunch of bars. So the next feature we want to look at on our calculator is called Binomial CDF. It's right underneath. And unfortunately, this is what Binomial CDF it does. It adds up the left tail of this distribution always without you asking. So you're going to put in the same things, NPQ, and NPX rather. Binomial CDF, NPX, same thing, same exact thing. And what this does is computes not only that one probability, but CDF stands for cumulative distribution function. It adds up that probability and every other probability below it. Okay, you clear on what it does? It adds up all of these in the left tail, which on this particular problem is in fact not what we want, is it? What are we trying to do? Remember here. Yeah, so we're going to do exactly what we said we would maybe do by hand if we were to do it by hand. We're going to do 1 minus Binomial CDF. What am I writing? 300.06. 25, right? 24, good, thank you, sorry. Okay. make sure we catch that. Why? Why? Because isn't this the exact set of stuff that we don't want? Right? Don't we want to add up 0, 1, 2, 3, all the way up to 24? Figure out what that is. That's exactly the stuff we don't want, and then subtract from 1. Okay? So that will give us something. I don't know what. All right, so here we go. Binomial CDF, 300.06, 24. Here, hold up. 1 minus that. So here it is. In one move, we got it. 0.0622. Okay, what do you think? You liking this? Permission fully granted to use this calculator feature, right? This is going to help us quite a bit. All right, I think this is our last problem. Let's see if we can at least get it set up before the bell rings today. 40 seconds? Did my clock that off? Okay, just kidding. All right. Wouldn't you have liked, though, to do something with volume leaks and widowed women? Okay. All right. We'll leave that one for the reading. One thing I might caution you about is the language in the problem. If it says more than 10, what does that mean? It's going to be a 1 minus again, but what probabilities are we looking for? We're looking for, 0 through, well, careful. If it says more than 10, what probabilities are we're wanting to add up to 11 and on, so you have to do 1 minus and up to 10. So just be careful the wording of the question. All right, there is a worksheet again, and I forgot to do it.
I feel good. Oh, is this for the public?
Do you like worksheets?
Yeah, because Claire just sent me out on the process, and it saves so much time.
When does, I tried to do like the one we did before about Alex with binomial CDF. It didn't, and I want to know if I'm just.
Oh, Josh! Let's talk about this. He's on your team.
So think about it. It's actually the same kind of problem we were just doing.
I was out yesterday, so here's the homework.
Okay.
Oh, no, this is homework 10. Alright, have a good day. And then this is homework 1 from like the day before.
Okay.
This is yesterday's homework that was due today.
Great, good.
Yeah, I wasn't here yesterday as well.
Okay. Let me get my books so I don't forget all these things.